Okay, so let's start the class and let's review the equation so far. Okay, so the amount of charge unit is coulomb, notation is Q, and then you have voltage. So remember, voltage is a property of 2 points. Okay, so it's the voltage of one point relative to the other one. So for example, if you have a 9-volt battery here, so you have a positive terminal, negative terminal, that means this one will be 9 volt. So the positive terminal will be 9 volt relative to the negative terminal. So you can think of the negative terminal, you can think of that as being the ground. Okay, you can think this is 0 and that will be 9 volt. Okay, so voltage is actually voltage drop is a property of 2 points. And then you can see here you have different batteries. So for example, if you have alkaline, it costs a little bit more, but it lasts longer. So sometimes it will say the capacity here, which means you can drain 550 milliamps for 1 hour. Or you can drain 55 milliamps, so 550 milliamps for 1 hour, or 55 milliamps for 10 hours, or 5.5 milliamps for 50 hours. That's what it means. You can see if you buy a mouse. If you buy a dollar store battery, it's okay, it's cheap, but it's not going to last very long, and you cannot drain as much current for the same amount of time. If you buy an expensive one, the lithium one, you see the capacity it's much larger. Okay, so what else did we see? We look at current. So current will be coulombs per second. So you can think of that as how fast the charges are moving in the circuit. And the thing that you have to understand, if I go back to my little circuit here, close the switch, you see, if I increase the voltage, so if I increase the voltage of the battery, it's very much like you are increasing the pressure. Okay, there is more pressure, so you are pushing the charge, okay, with more strength, and you see the charge are moving faster, so it's delivering energy, okay, faster. So it means the power will be larger because power is energy per unit second. Okay, so that will be the current here. That's how you measure current. The unit is amps. Coulomb, amps means coulomb per second. It means that you have 6.5 coulombs of charge per second, okay, going through this. Is that clear? And then you have voltage. Voltage is like pressure. Okay, so in the homework due tonight, you can use those equations. And then we talked about power. Power is the energy consumed by a load or produced by a power supply per second. The unit is watt, James Watt, and it's actually joules per second. And then we're going to introduce a new physical quantity called the resistance, and the unit is going to be ohm. You see, it's like a omega, like those expensive watches, right? So if you don't remember, you can think of yoga when you do ohm. Okay, so that will be the unit of resistance. So today we're going to talk about that physical quantity here. We did that. Okay, we did that, we did that, we did that, we did everything here. Let's talk about resistance. And let's take other examples you might be more familiar with. Imagine you have a reservoir of water here above the ground. As you increase the height of the reservoir, what's going to happen to the pressure of the water? Does it increase, decrease, or stays the same? Higher up, that means higher pressure. Does that make sense? So that's why New York City, you know, those tall buildings, you have those ugly reservoir at the top of the building to make sure you have enough pressure for all the floors, right? So higher the reservoir is, more pressure you're gonna get. More pressure means the water will flow faster. So there is a relationship, okay, linear relationship between how fast the water is flowing and the pressure of water. Is that clear? And then you can control. So that will be for a given size of the pipe, but you can control the amount of current, not current, water flowing by changing the size of the pipe. Does it make sense? So, for example, in chemistry, maybe you take a thermodynamics class or a unit about thermodynamics, and you know that heat always flow from hot reservoir to cool reservoir. How much heat is flowing depends on the difference of temperature. So it means if it's very cold outside, I heard that in Illinois it's minus 20 degrees Celsius, and very hot inside, you're going to lose more heat. Okay? So as you increase the difference of temperature, you're going to increase the flow of heat. Is that clear? And the amount of heat also, you can control that with the types of windows that you use or the roof, right? So in electricity, it works the same way. You're going to have the voltage drop across, for example, this component, we call that a resistor. Okay, so you can have a voltage drop across it, which means it's like pressure. Okay, and if you increase the voltage drop, if the voltage drop is increased, the charges are going to flow faster. So you're going to increase the amount of charges flowing through that resistor. So it means there is a proportion, it's a linear relationship between the voltage and the voltage drop and the current flowing. Does it make sense? You increase the pressure, you're gonna have more current. Okay, so the charges are gonna flow faster. Can you control the amount of current flowing? Yes, we can do that by controlling R, which is called the resistance, and the unit is in ohms. Is that clear? So probably you are more familiar with this, but it's the same idea. Okay, so let me show you what I mean. Okay, so let's take a circuit here. Okay, so here I have a load. I'm going to remove that load. I'm going to have what we call here a resistor. Okay, a resistor has a resistance. And you see here it says 10 ohms. So the current here, I'm going to take a voltage, maximum voltage of 120 volt. By the way, in the pop quiz, if I ask you, you know, what's the voltage from the outlet? Remember, I didn't get electrocuted. That's why you still have a physics professor. Do you remember what was the voltage here? Very good, 120 volt AC. So that means the current doesn't flow in one direction. It goes back and forth, back and forth, back and forth, right? So that's why it's called AC, alternating current. So anyway, 120 volt here. What's the current? 12 amps, right? Which means 12 coulombs, 12 little marbles, if you want, 12 little 1 coulomb, okay, being burped by the power supply every second. Now, I can think that that's too much current. 12 amps, it's a lot of currents. Maximum in a house usually is 20. 10 amps can kill you. A few amps can kill you. So I can think that that's too much. And I can increase the resistance here, and I can slow down those charges. So I'm going to have less current flowing. You see how it works? So let's go back to 10. Luckily, that's a simulation, so I don't take any chance. And here, I'm going to take my... So you see, when you are measuring current, it has to be part of your circuit. So this is called the ammeter, is to measure current. And the resistance here is like nothing. It's like 0, so you don't disturb the current. So anyway, I take my voltmeter here and I'm going to measure what we call the voltage drop. Okay, so voltage drop, and this is a resistance of 10, okay, and the current is 12. What do you think is the relationship between the voltage drop, the resistance, and the current going through the resistance? How do you go from 120 volt? Okay, the current is 12 going through it, so 12 amps going through that resistor, and the resistance, which is it's like a blueprint, like you say you have blue eye, so this one has a resistance of 10 ohms. What's the relationship? You see, voltage 120 equals so 12 times 10. Very good. Okay, that's called Ohm's law. It means that the voltage drop across a resistor equals to the resistance, which is like printed on it, okay, it's the blueprint, times the current going through it. Let's verify that it's always true. Let's take a resistance of 48 amps. Let me take, I want to take ohms. So what's the resistance here? 48 ohms. The voltage didn't change because I didn't change the power supply, still 120 volt is available. What's the current? 2.5. Can you take your calculator and do 2.5 times 48? 120. Okay, so that's what we call Ohm's law. What does it mean? It means that the voltage drop across a resistor equals to the current flowing through it times R. So if you draw it this way, you see all you have to do, voltage drop equals Ri. So it's called the Ohm's law, and it's not a nature's law. So it means like nature's law means F equals ma, it's always true in any part of the universe. But this is only true for those type of laws. If you take, for example, a LED, which is a semiconductor, V equals Ri is not going to be true. Okay? Is that clear? Now, if I take, I'm going to take two loads, something interesting. So pay attention because you never know. Someone is calling me. It's my birthday. Thank you. I cannot tell you my age though. So I'm going to take one here, which is 10, and the other one will be 30. I'm going to take 30. So this one is 30 ohms, this one is 10 ohms, right? So this one has a larger resistance. So if you have it alone, that means it can reduce the current more. Is that clear? So let's verify. So when you multiply, when you do the voltage drop, it's really across. So what's the voltage drop here? 90. Let's see if it makes sense. What's the resistance? 30. And times, you have to do it with the mouse. You need like the password. I don't have the password to change it. That's why. So if you do voltage drop is 90, what's the current flowing through it? 3. So 3 times the resistance is 90. That will be what we call Ohm's law. Now, if I do it here, voltage drop across. So do we have 90 or you have less here? Less, because the resistance is 10. So 10 times 3 is 30. So you don't want to have that kind of in your house wiring, because turns out the load with the most resistance will take all the power, right? So all the voltage goes across the resistance with the most resistance, the resistor with the most resistance. Is that clear? Yes.
You have two resistors. You add them up and then multiply by the current to get the total voltage, right?
That's a very good question. So here you have 30 volts, right? Let's find the voltage drop here. What do we get? 90. How much is 90 plus 30? 120. But how much is the resistor again here? 30, and here is 10. So let's check something. What if I replace this one, 10 plus 10 plus 30, how much is that? 40. So you can replace your two resistor by one, okay, and you get the same thing. So instead of having two resistors, okay, 130, 110 ohms, you can replace that by a single one, okay, which is called the equivalent resistance, and its value will be the sum of the two. Does it make sense? And now if I do the voltage drop, it's going to be 120. Okay, so electric circuit in a nutshell, it's very important for the medical field, or if you do research in biology, for example, looking at the cell can be modelized. You can have a model with an electric circuit. Okay, so all our nervous system works with electricity and voltages. Okay, so, but that's a resistor. So let's go back to before. I had 30 here. And I had 10. Remember, I had 10 here. Do I need to have a resistor? So resistors are special components that we use to control the current flowing. But any load that we have, like this light bulb here, you see, you're gonna get the same thing because it has its own resistance. Okay, so you have a 10 ohm resistance here, and then you have a 30 ohm resistance. So most of the loads, okay, has its own resistance. Does it make sense? And you can apply Ohm's law. So again, here the resistance is 30. 30 times 3 is 90 volt. And then here, you see you have 10. This is a 10 ohms resistance. Okay, I measure the voltage drop, and you have, forget about the minus it, because the red is supposed to be on the side of the plus, but 30 equals 10 times 3. That's how it works. But the issue with that is that, for example, I can replace this one, I can replace with another load here, okay, and I can change here with a 30. And this is not right. You see, the one with the 30 ohms is brighter. It's not supposed to be because it has a larger resistance, but it is brighter because of Ohm's law. It's taking most of the voltage, right? So you have 30 times 3 is 90 volt. This one has a small resistance, So it's supposed to be very bright, and it's not, because it doesn't get the voltage it needs. It's very upset. Okay, so you have 3 times 30 is no, 30 equals 3 times 10, because of the resistance is 10. So that's why in the wiring in a house, you never have that configuration. It's called the configuration in series. Okay? Because now if I have them, I remove this one, go away, and I have only the one with the large resistance. Larger is the resistance, dimmer it gets. Which means if you have a 100-watt light bulb and a 40-watt light bulb, which one is the brightest if you just connect to the outlet? 100 or 40? 100 watts or 40 watts? If I give you the choice, can you touch a 100 or a 40 watt? 100 watts is consuming more energy, right? So which one is the brightest? No. Yeah. If you buy to the store and you have the choice between a 40 watt and a 100 watt, which one will be the brightest? 100. Okay, because it's consuming 100 joule per second. Does it make sense? Okay, go do the experiment yourself. Okay, buy a 40 watt and you buy those lamps, cheap one from the dollar store. Like the stand here, you put a 40 and a 100. Of course, 100 will be the brightest, right? Is the voltage the same from the outlet? Yes, for the 40 watt and the 100 watt. So the voltage is the same. So that means if the bulb is the brightest, like 100 watt is the brightest, that means it has more resistance or less resistance? Less resistance, okay? Because then you have more current, okay? More current for the same voltage means the power will be the largest. Do you understand? So you don't want to have a 100 watt and a 40 watt together, because the 40 watt is going to steal everything from the 100. 100 is supposed to be brighter, which means it has a smaller resistance. Is that clear? So for example, let's take this one. What's going to be 120 ohms? Okay, 120 ohms. What's going to be the power? What's the wattage? Let's review what. What's going to be the energy? Do you remember the equation for energy? Let's go back to the equation. How did we define power? Energy consumed per second. It's going to be the V stands for voltage times current. Okay, so here I have a load. Let's go back to my load. What's the voltage across it? 120. What's going to be the current going through it? 1 amp. So what's going to be the watt? 120 watt. 120 watt. Very good. 120 watt. Is that clear? So it's going to be the voltage across it times the current through it. Is that clear? Yes? Now, if I take, and you see how bright it is, if I take another light bulb with a smaller resistance, ooh, I start a fire. Start a fire. Okay, how much watt do I have now? The resistance is smaller, the current is 10, so 10 times 10 is about 100 watts. So you're going to have more watts here because the resistance is smaller, right? If you have no resistance at all, that's what is called a short, and the current here is infinite. So it means no resistance, the current can flow faster, you have too much energy delivered. Is that clear? Any question? So I highly recommend that you play with them to have a gut feeling, because it's so important to understand that. So that means that if you have a large resistance, less wattage. Okay. So let me show you very quickly here. So I have a simple circuit. So that will be the, how do we call that? The power supply. What's going to be the voltage here? About 1.5 plus 1.5 plus 1.5. That's going to be 4.5 volt. So 4.5 joule per coulomb. Okay? So the current, the positive charge is going to flow, deliver the energy in the light bulb here. Okay, the light bulb is very happy, and here I can measure the current. So the current is, you have to look at that scale here, is about 0.3 amps. Okay, do you see how bright this is? It's very happy. And now I'm going to introduce some resistance. So here I have resistors. Okay, so I have 5, 10, 15. I'm going to skip the 5 because the 5 has such a small resistance that it will get very hot. So a load is always a way to transfer energy. So that turns energy into light and heat. A resistor turns energy into heat. Okay, so it's made of carbon, and you can burn your finger. So I'm going to skip the 5. Oh, did you look at the current here? Do you see it's about 0.3? Can you all see? Okay, so now I'm going to introduce a 10 ohms resistance. Is it happy? Not as happy as before, because instead of having 4.5, some of it will go to the resistor, some of it will go to the load. Okay, so even though the current is the same everywhere, the voltage drop is not. So if I want to measure the voltage drop, let's see if I have the voltage here. Can you see? Because it's hard for me to see. Yes? Okay, so let's see. What do we have for the power supply? I have about, see, I already consume a lot. It's about 4.1 volts, right? Let's see how much this one is getting. It's not very happy here. 1.45 volt. So does it make sense to you that across the resistor, I'm going to get 4 minus 1.45? Right? So let's see. Across the resistor here, I'm going to have 2. It's about 2 volts, right? So if you add this voltage drop plus that voltage drop, maybe some here, you're going to get the power supply. But you see that the resistor is stealing some voltage from the light bulb. So what do you think is going to happen now? I'm going to go to 15. Now do you see? It decreases even more. It's even more upset. And now the voltage drop here across the resistor is about 2.5. Can you see that, or you can see that? It's about 2.5, right? So it's taking away even more voltage because the voltage drop is proportional to the resistance. So this one is crying because you see it doesn't get enough voltage. Now it's like 1 volt. Now if I increase the resistance even more, so now I go to 20. Okay, so that's a resistor of 20. So you see, I decrease the current even more, and you can barely see the light bulb. It's there, but it's very dim. Okay, that's because the resistor here is taking all the voltage drop. So you never have that in a house. You cannot have your microwave connected to your audio system, connected to your oven, because one of them will take all the voltage. So this here, if I measure that, we see how much, do you see how much? 2.97, okay? So as you increase the resistance, the current decreases. Is that clear? Okay, so let's go back to Ohm's law. Ohm's law says that the voltage drop across a load or a resistor will be equals to the current going through that load times the resistance. So you can use the resistance as a way to control the amount of current, to make the current go slower. So if you like thinking of a hydraulic system, you see if you have a smaller pipe here, you're not going to have as much water that you have here. Right? Make sense? So again, this is very much the same idea. The voltage drop, okay, is proportional to the current. If you increase the voltage drop here, the current will be larger for the same resistance. Or if you have a given voltage and you change the resistance, as you increase the resistance, the current will be less. Okay, so since you're in biology, so this is called, do you know what it's called? A neuron, very good. Okay, it's like a nerve fiber, and it's part of our electric system. That's how a signal, like for example, if you touch something very hot, there is a signal traveling up to my brain. Brain says, "Remove your hand, dummy," and that's what I do. Okay, so you have the signal moving, and what is moving actually? It's not electricity, it's not current, but it's voltage. So for those who are interested, there is this very nice video on YouTube that explains how it works. But basically, you see you have this cell here. That's here that you have the synapse happening. So this is a neuron. And the signal will be a change in voltage moving along the fiber. So, for example, when there is no signal moving, you have ions like magnesium, electrolyte, potassium, calcium, chlorine, they move in and out the cell. So, for example, when it's at rest, no signal is traveling. You're going to have minus here and plus there. I'm sure you learned that in biology. You have little channel opening, and ions can move in and out. And because this is plus, this is minus, that means you have a voltage. And if you measure your voltage here, that's going to be 70 millivolt lower than here. Okay, so when you have a signal moving along your nerve, right, the fibers, then you're going to have a change in voltage. So ions come in and out, so there will be a change in voltage moving from here to there. And when it gets there, you have neurotransmitter, chemicals, to communicate with the next neuron and so forth and so on. But it's an electrical system. That's why it's so important to understand the electricity. That's why I start with that. Then my point is that when the signal is moving, you don't want to have any leak. Okay, you don't want to lose the signal to another part of the body. That's why you have a very thick layer around there, right? It's called the myelin. myelin here, and that's a resistance. Okay, so that means same way here you have electricity flowing, or you have a signal flowing in electric wire, and you're going to have an insulating layer, right, with a very high resistance to make sure that the signal does not leak out. So here it's the same idea. Okay, so it's like a protective layer that prevents the signal to leak out. And this layer is made out of cholesterol, actually. So that's why cholesterol is not bad. It's a good thing. You want cholesterol to have a very good, nice layer, especially for the brain. So you need cholesterol for the brain. Okay. So that's a connection, because I know many of you are in biology. So let's, okay, so this is called here neuron action potential, if you want to look at that tutorial. So now let's go back to my circuit. Imagine you want to build a circuit with a power supply. You want an ammeter to measure the current. You want a voltmeter to measure the voltage across the lamp, and you want a lamp. How would you do that using schematic? Okay, so for example, the circuit that I had here, how can you represent using those symbols? Can you try to do that? So you use that, and you want to have, for example, let's put a battery. So that will be the symbol for a battery. Okay, so what you do is long leg is positive, short leg is negative. Okay, so that will be your positive terminal, negative terminal. And here you say, okay, that will be a 9-volt battery. Let's say it's a 9 volt. So I put 9 volts here. Then somewhere I need a switch. So you can draw the switch here. And then here, maybe, so the order does not matter. It's commutative. Remember in math, when you learn about commutativity, it means 2 times 3 is the same thing as 3 times 2. So same thing, doesn't matter which one you put first. Maybe I'm going to put a lamp here, so that symbol for lamp. Maybe I'm going to use a resistor to protect the lamp, because I don't want too much current, okay? Otherwise it's going to fry it, okay? What else do I need? I need a device to measure the current. And that device has to be part of your circuit. So I'm going to be part, place it here, and then I close the circuit. Okay? And second thing you do, when you close the switch, you want to show that the current is flowing this way. So you will do it this way here. Okay, so it's flowing because we like Benjamin Franklin. Even though it's electron flowing, we're gonna say it's positive charge. Positive charge is flowing. Okay, and then let's say you want to measure the voltage across the resistor. So imagine that it's really a voltage drop that you are measuring. Okay, can you stop being on your phone? Someone is on the phone. So you are measuring the voltage drop here. Is that clear? So maybe that's going to be voltage drop 1. That will be voltage drop 2. And V1 plus V2 will be equals to 9 volt. And here you are measuring the current. It could be in amps, or it could be in milliamps. Is that clear? Okay, so most important is to understand the concept. So for example, can you measure the current here? So I'm going to show you the best way to make sure you get those questions right. Okay, and it's going to be very useful when we get to circuit in series and in parallel. What is it available? You have a 1.5 volt power supply, so 1.5 joule per coulomb, and the current is flowing in this direction because this is plus and this is minus. Energy is delivered to the load, 1.5 joule per coulomb, and then it's coming back here, and then it gets to boost again. If you want to represent that, of course, you can do it the way I just show you. You know, you have the battery here and you have the lamp, and that's all you have. You don't even have a switch. So 1.5 volt. Here you have a lamp and it's 20 ohms. But I want to show you a different way that we're going to use. You're going to do it the engineering way. So you're going to say, okay, I have 1.5 volt available. So think of that as height. Okay, so is 1.5 volt relative to the ground. And then what's going to happen? I have only one load. So that load, I'm going to make a resistance here because it's easier than the lamp. So it's like a resistance here. I'm going to say this is 20 ohms, right? And then you go back to base. So this is my base. I'm going to use that. We're going to see why, because it's going to be easier to solve the problem. And then you see it's like a pipe. You go from high up to ground. So this is ground, okay? In electricity, it's called common ground, COM on your voltmeter. And imagine you have water flowing here, I. Once you have done that, it's very easy to use Ohm's law because you're going to say, okay, so this is the voltage drop. How much voltage drop? 1.5. And then here you put a times. So when you use Ohm's law, you're going to say 20 times I equals 1.5. Because Ohm's law equals the voltage drop across the load equals the resistance times the current going through it. Voltage drop is 1.5. It's falling 1.5. That was for people who are falling asleep. And so 1.5 equals 20 times I. So what's going to be I? 0.0. How many zero? Is that right? Yes? Okay. In milliamps, you multiply by 1,000, so it's going to be 1, 2, 3. So it's going to be 75 milliamps. Is that clear? Oh, I forgot to tell you. And don't space out. Okay, I see people on their phones. Very annoying. But do you remember the book I'm recommending from Johnson and Cutnell? It's called Physics. Okay, any edition is fine. That's where my slides come from. So we are doing chapter 20. So you can get it in PDF. But you see, it's exactly the same slide that I'm using. Okay, and it's very good if you want to go in the medical field. It has a lot of connections. See? Oh, look at that. That will be the next chapter. No, next chapter for us, but in the book here it's chapter 19. So we are doing chapter 20, and you see it talks about voltage. They do that experiment in AC1 next to my office. I don't know if you know that lab. It's called the egg lab. So they have you do weird stuff, maybe not a pinball a machine, but sometimes they make you go on a bike and they see which area of the brain is stimulated, and that's about voltages. Okay, so that's the book I recommend. So let's go back to the slides. Here, so Ohm's law, the voltage drop across a load equals to the current going through it times the resistance. What does it mean? It means that for a given resistance, the voltage is proportional to the current. Example, Here you have a voltage drop of 3 volts, and the current through the resistor is 1 amp. So if you multiply the voltage by 3, what do you think the current is going to be? More voltage, more pressure, right? So if you increase the voltage, what's going to happen to the current? It's going to increase. So it's going to be 3 amps. It's a proportion. Okay? That means it's a proportion. For the same resistance, if the voltage is multiplied by 3, the current is multiplied by 3. Typical question, conceptual question for the test. My test is never heavy in math, but conceptual questions, I like them. Okay, so it's a proportion. Multiply the voltage by 3, the current is multiplied by 3. Is that clear? Because you increase, it's like increasing the pressure. Okay, you are pushing harder on the charge. Okay, so this is Ohm's law. Okay, so let's try to do this one so you can talk to each other. So that's a circuit in a typical electric or a flashlight. Okay, so you have your load and you have 2 batteries in series. Okay, so this is plus, minus, plus, minus. So each one of them is 1.5 volt, right? So each one of them is 1.5 volt. What's the power supply do we have? 1.5 and 1.5? 3 volt. Okay, so that connects you to the, if you want to do a demo, for example, you can take a flashlight apart if it's possible. You will see the power supply and you have a closed circuit. Look, 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 the current inside the filament come back to base. So this is my base here. Okay, imagine this is my ground. The charge get a boost. 3 joule per coulomb goes through the little filament here. It's so thin. It gets very hot. So hot it's going to emit light and then it comes back. And here you have a switch. Isn't that great? Okay, go. So the question is find the current. You can help each other. More you do in class when you have less you have to do at home. I'm going to do it the way I was introducing. So you have a power supply of 3 volt, okay, and you have a load. So I'm gonna draw the load like this because it has a resistance R, okay, and then it comes back to the base, okay, so it's 3 volt relative to the base. So this is plus, this is minus, and you have current flowing, and it says it's 0.4 amps. In between, you put a times here. Do you see Ohm's law? Okay, so it's going to be 3 equals 0.4 times R. So how much is that? Huh? 1 point? Oh, 1.775. No. Oh, 0.75. 7.5. 7.5? Oh, okay. Thank you. 7.5 ohms. Okay. Now, if you want to do the other schematic, so you will say, okay, I have 2 cells. So one is 1.5 volt, the other one is 1.5 volt. Maybe I'm going to include a switch here. And I have my load, which is a lamp. And I'm going to close the circuit. So that's my switch. And then you see that the current is flowing always from plus, back to minus. Okay? Easier. That this is what we call the engineering, I call it the engineering way, because it's easier to solve the equations. Okay, so here you have a cheat sheet, but I don't know if it's very useful. The relationships between all the equations we have done. So make sure that you print out your equation sheet, okay? So let's try to do this one. So LED, do you think LED I can apply Ohm's law? No, because the LED is a semiconductor. So they behave, they have their own way to behave. Okay, so it will you will have to look at a graph. So it doesn't obey Ohm's law. Only resistors obey Ohm's law. Okay, and it says I want to make a circuit. LED are very special because they are willing to work with a very itsy bitsy tiny current. So that's why it doesn't consume a lot of energy. But it needs at least a voltage of 1.7 volt. Otherwise, it won't lit, red LED. But you have to be very careful because if you go beyond that amount of current, the LED will fry. So you don't want that. You don't want too much current for LED. So that's why you need a resistor to protect it. Okay, to reduce the amount of current so LED is happy. Are you with me on that? So let's see what's going on here. Let's look at that question. Yeah.
So it needs a minimum of 1.7 volts?
Yes. So it's a red LED. It won't work unless you provide 1.7 volt. So if you take a 1.5 battery, for example, with a LED will not lit because it doesn't get 1.7. It has to do with quantum physics, right? It's a gap. It needs a gap of 1.7, otherwise it says no way, right? So the voltage drop across a red LED is always 1.7 volt, okay? And the current, the maximum current of a LED is 20 milliamps. So we want to find out what's going to be the value for the resistor such as the current is 20 milliamps or smaller and the voltage drop across the LED is 1.7. Do you understand the question? Now, the best way to do it is to do it the engineering way. Let's do it this way. How much voltage is available to begin with? So it's like a height. What's the voltage of the power supply? 9 volt, okay? So you start, it's like 9 yards, okay? It's like a height. And then what are my loads? I have a resistor, R, that I don't know. And then here I have a LED that does not obey Ohm's law, so I don't put a R here. However, what do I know? I know that the voltage drop across the LED, so it's a drop, it's like you are taking a tape, measuring tape, the height, you are measuring the height. The height is 1.7 volt. Are you with me? And you know the current, okay? You know the current is 20 milliamps because that's the maximum current, 20 milliamps. 20 milliamps you divide by 1,000, which is 0.02 amps. Okay, so now my question is find R. Okay, so can you help each other, talk to each other? Okay, for R is a resistor. Okay, so if it's a resistor, that means it obeys Ohm's law. It means that you have a relationship between the current going through it and the voltage drop here across it, right? So you have V equals Ri. Okay, so can you talk to each other? How do we do that? So what? So can we find the voltage drop here? So the total height is 9. 7.3. Do you all agree with that? It's like you take a measuring tape. So the height here is 1.7, total height is 9, so you have 7.3 volt across. It's across, right? The resistance R. Is that clear? So can we use Ohm's law now? We know the voltage drop across R. We know the current going through it. And the question is find R. Okay, so the resistance here is unknown. You know that 0.02 amps and the voltage is 7.3 volt. So I'm going to apply Ohm's law. So can you find R? Huh? So V equals Ri. What's the voltage drop across R? 7.3. R times what's the current going through R? Very good. So the resistance will be 365 ohms. So it means if you have a circuit like this, you better use a resistance of at least 365 ohms to protect your LED. So what's the goal of the resistor is to make sure the current is limited to 20 milliamps, because if you look at the data sheet, you know that the LED will fry if you go over 20 milliamps. Is that clear? Okay, so very important if you, work anywhere, medical field, you don't want to be electrocuted. So everywhere we use resistors. So that used to be the integrated circuit. So now they do everything miniature, but you can see, does this one look like that one? What's the difference between this one and that one? What's the difference between this one? Look at them. Yeah, they have the same shape, but they don't have the same colors, right? Did you say colors?
I said the color, but I thought it was a dumb answer.
No. It's the colors, right? Yet there is a color code. So it used to be that students had to learn the code. So I don't know, red is for 100, this one is for tens, and so each color is like 100 and then 10, so 125. But nowadays we have those devices, so we can measure the resistance. Let me show you quickly. So I have Amanda and Nathalie. So you see here, I don't know if you can see, I go here, it says ohms, omega. Where is ohm? Here it's ohms. I go to very small. Can you see it here? Okay. So what you always do to measure the resistance, you go, oh, look at that, it's still close. Okay, so you take the resistors out of the circuit and then you measure like this. So for example, this one, if it doesn't move, what do you read? 15 ohms. Do you see that? If I take this one, and usually it doesn't say how much it is. You see, how much is that? 20, about 20. And more resolution you have, more expensive they get. So a cheap one like this one, it's very cheap. You have like 10% margin error. If you want to have more precise electronics, so you can buy them at 1% error. margin, and of course they are more expensive. This is also a load, so I can measure also the resistance. It's hard to do two things. It's about 20. If it stopped moving. Okay, I'm gonna do two things at the same time. Stop moving. Very annoying. So what you usually do, you have to use connecting wire so it doesn't move. Okay. So what do you read? About 2. Okay, it's 2 ohms. So very small resistance. You see how it works? Can I apply Ohm's law to an LED? No, right? It's a semiconductor. So anyway, you have codes here. You see brown, black, orange. I forgot the code, but it will tell you the value of the resistor. And nowadays we make it on a waffle, right? Silicon waffle, so everything is very small. You have LED here, and that's gonna be, I don't know what it is, like another integrated circuit. Okay, so maybe that's gonna be on one of the lab. Okay, so you have, what is that? What's the symbol? Measuring the, oh, sorry. So here's the experiment that you're gonna do during the lab. So A, what is this? Very good. Ammeter to measure the current. You have a resistance here of 1000 ohms. K stands for 1000. And you have the voltage. And as you change the voltage here, you increase the voltage. So that's a special power supply. You can change. You have a knob here, and you can change the voltage from 0 to 10 volt. It's a DC power supply. And as you increase the voltage, you increase the pressure, you're going to increase the current. Do you see the relationship is linear? You see, for a step of 1 volt, you increase the current by 1 milliamps. Okay, when you go from 4 to 5 volt, that's a step of 1 volt. What's going to be the step in milliamps? It's also 1. Okay, so then we ask students, I mean, when I was teaching lab long time ago, it's called the Ohm's law lab. You do a graph that will be the current here in milliamps. Here you're going to have the voltage here in volt. For 0, you're going to have 0 current. For 1 volt, in that case, you're going to have 1 milliamp. For 2 volts here, you're going to have how many milliamps? 2 in that case, okay? And you're going to have a linear relationship. And if you find the slope, delta y over delta x, you see that on the y-axis you have 1. A step of 1 is a step of 1 milliamps. Okay, so the slope equals 1 over 0.001, which is 1000. And 1000 is the resistance. So all that to say that the voltage is proportional to the current, and the constant of proportionality is R. R is the slope. V equals Ri. So it's like a linear relationship. Y equals mx. M is the slope. Here you have the voltage drop. equals resistance is the slope times the current. Okay? At some point, you're going to do that lab. Okay, that comes from the book I was telling you about. So this is non-invasive, is to check if people have what it's called clots. What it's called? Thrombosis. What is it called? Thrombosis, right? Thrombosis, right? You learn that, right? In biology, anatomy, or something like this, right? Thrombosis. So instead of having an invasive procedure, what they do, they have current going through it. So you have two electrodes and you have a source of current. So you have the current and you measure the voltage between the electrodes. So you have the voltage drop, you have the current that you master here, you can control. So you are measuring using ohms law, you're measuring the resistance. And the resistance here will be depending if you have clot or no clot. So by measuring the resistance here, it depends on the length, then you can measure if you have clot or not. That's because as you breathe in, breathe out, the volume of blood, it's going to change. So the voltage here is going to change. So you can find the relationship between the voltage drop, the current, and you know if you have possibly clots. And then if you do have, then they do have, then you have to do something more invasive. Is that clear? So just to show you that anything with electrodes, it goes by pairs, okay? Because a voltage is a property of 2 points. So when you do EKG, for example, 2 electrodes, right? 2 electrodes. You have those machines for when you have a back pain. For example, they put all kinds of electrodes on your back, but it's always by pair, a plus and a minus, a plus and a minus, right? And in between, the muscle is going to contract because you apply a voltage. Okay, so let's do a problem here. So power, remember, is always voltage drop times current. So this is also true for a power supply. However, if the load is a resistor, so then you can replace voltage by Ri, and you have these equations here for the power. Okay? So that means that if you have a resistor, okay, and you have a voltage drop, and you have the current going through it, then you can apply Ohm's law, V equals Ri. And you also know that the power, which means the energy consumed by the resistor every second equals VI. Do you agree with that? Okay, so this is always true, even for power supply. But this is true only for resistor. And then you can play with those two equations. You can replace V by Ri, and you're gonna get Ri squared. So that will be the energy consumed by the resistor every second, only true for resistor. Or you can substitute I by V over R. So that will be V squared over R. So you don't need to memorize those. Only look at your equation sheet. You should have V equals Ri and P equals Vi, and then you can play with them. Is that clear? So for example, if you go back to here, can you find the current flowing through that circuit? It's a car battery and it provides the power for your headlight, for example. So this is a 40-watt light bulb. What's going to be the current flowing through it? You just apply the equation, right? Nothing hard here. Okay, so V equals, power V times I. So let's say you have plus here, minus here, the current is flowing through the load and then come back. So 40 watts light bulb, it means it's consuming 40 joules per second. Okay, so this is called the wattage. It's going to tell you how much it's consuming. If you have a microwave, for example, it's consuming a lot of energy. So it's like 1500 watts, something like this, or 2000 watts. 40 watt is dim, it's not very bright. So what you get, so 40 equals 12 times I. So the current equals 3.33 amps. Okay? So this is the outlet, 120 volts. You have 100 watt light bulb. Okay, so it's going to be a very bright light bulb. It's very hot. Plus, it's the old light bulb. It has been phased out. It's the incandescent light bulb. So anyway, that will be 100 equals 120 times I. Is that right? No. Yes. Which is? Right, 0.83 amps. Tell me your name. So it's going to be multiplied by 1,830 milliamps. Is that clear? So this one is a load with a resistance R. So if I want to find R, okay, let's say, of course, I can use Ohm's law. Okay, I can say 120 equals Ri. Is that clear? But if I am given the power, then I can use that equation here. You see, power for a resistance is V squared over R. So the power, the wattage is 100 equals 120 squared over R. And you can find R, right? You cross multiply and then divide. Ohms. Or you can use Ohm's law. You will get the same thing if you have I. Is that clear? If you have any questions, so about safety, remember that the electric current always choose the path of least resistance. So it means if you make a circuit like this, okay, and if you give the choice to the current, to the charges, to the electricity to flow through the load or avoid the load, guess what? It's going to avoid the load. Okay? Current always like to flow through the path of least resistance. And if you just happens to be the path of least resistance, it's going to flow through you. So for example, if there is a leak somewhere here, you touch it, so you have electricity here. Ooh, why do I have to bother going through the resistance here when I can go straight to the load, straight to the ground, okay? Because the water here is connected to the pipe is connected to the ground. So that's very bad, don't do that. I can show you that here. Okay, okay, so that's happy. Nothing happens special there. But if I make a short, if I give the choice, for example, to the current to take a shortcut, okay, so make a shortcut here, it will go through the path of least resistance. It's not going to bother going through that. It's very tiring. It goes back to base quicker, right? That's what we call a short. if you put your two fingers, which of course never do that, but if you take your two fingers in the outlet, one finger in the hot, the other one in the return path, of course you're going to be electrocuted, so you don't want to do that. So same thing here. If you have a machine and it's not here, you have a plug, and these are the old plug with only two holes without connection to the ground. If there is a leakage somewhere in the machine that you are using, okay, it will go through you because that's the way it goes back to ground. So in a house or in a hospital, for example, how does that work? You have a transformer somewhere outside, okay? So it's going to take a high voltage, 1000 volt, for example, bring it down to 120 volt, okay, available to your house. And to go back to base, it has to go through the ground. So it's very much like I told you in a car, the return path is the chassis of the car. That's the way the charge goes back to the battery. So here you have your transformer. It's like a huge power supply. The electricity will go through the ground to go back to base. So if you happen to be here and you touch that, okay, it's going to go through you to go back to base, to go back through the ground. You see how it works? There is a reason for that, why it's connected to the ground. You see, it's always connected to the ground. At some point, even the return path, you see the return path, so this is hot, this is the return path, also connected to the ground. Why is that? Because if there is lightning hitting the transformer, can happen, the electricity will flow to the ground if there is a connection to the ground. If there is no connection to the ground, well, lightning will go into your house. So that's why the return path is the ground. Is that clear? So if you're gonna work in a hospital, I think there is a very nice website. See, it's still there, and he tells the story how he worked in a hospital and he got shocked because somewhere there was a leak here, right? So the electricity, instead of going through the load, it went through him into the ground. So he talked about safety and he explained how it works. That's why if you work in a hospital, if you have to touch all those machines, make sure you use those very thick shoes like Croc. Okay, Croc are not bad, kind of work, but don't use flip-flop, for example. Okay, you want like the bottom of your shoes to be like rubber, so you are kind of isolated. Of course, if the voltage is too strong, it's not going to prevent electrocution. So he talks about that. Of course, you don't want to have wet hands. That's not a good idea. But that's how it works. Okay, so I recommend that you go on that website. So, for example, if someone touches a hot wire, okay, the hot line is gonna be in trouble, of course, because he is a path to the ground. And if someone touched that guy, he will be also electrocuted. So they have to use a different way, right? He has to use some insulator to pull him away from the hot line. So the idea is that electricity likes to go to the ground. So if you have an outlet, you always have a hot, the hot connection. So that will be the small hole that you see. That will be the neutral path. So usually it's safe, but you never know because it's supposed to be connected to the ground at the end, but sometimes you still have some leftover voltage drop, and this is safe. This is connected to the ground. So one thing that we used to do, like if you work with sensitive laptops, for example, you can fire your laptop if you have too much static electricity. And I don't have what I was supposed to have. Ah, yes, I have. Yeah. No, that's not the right. Yes, yes, it's here. So if you want to remove your static electricity, what we used to do, you have a special bracelet here, like a rubber bracelet. You attach that and you connect that to the ground to remove the static electricity because the third hole is the ground. So let me demonstrate. You see here the outlet. Okay, so the small is the hot, so you don't want to put your finger into that because otherwise you're going to make a part through the ground. This is the return part, also connected to the ground, but you never know, so not safe. Yeah, it's safe. Okay, so you can do this, and I'm not dead. Yet. Because that connects me to the ground, so there is no charge flowing. So if I want to remove my static electricity, I do this. If I pick up electricity from the ground, here all the electricity will go to the ground, right? So I remove my statics. That, but if I do that, you will not have a professor. You will have to find another one. So it's the third one, right? The one below. But don't try. So just to be safe. But it used to be that the plug had only two pegs, right? The hot and the return. That was not safe at all. Nowadays, they have a hot here connection. So if there is a leak somewhere, instead of going through you back to base, if there is a third plug, which is neutral, it will go through the ground, into the ground. Do you understand? Okay, so if you have two holes only, or only two connectors, that's bad because if you touch it, you make a path to the ground, go back to base, you are electrocuted. If there is a third connectors here, connection goes to the ground, then you are safe. Yes.
Well, I think you just kind of explained it when you said if it has two prongs, then
Not good.
not good. So, for example, for European Union, and I think Africa also uses it, outlets, you would be toast. Basically, if you touch the outlet.
Oh, okay, no, it's another. So in Europe, that's because instead of having 120 volt, they have 220 volt. But they also have a neutral. They also have a return ground connector. Okay, so in Europe, oh, that's the whole story. You have to blame Thomas Edison. Thomas Edison decided that voltage was very dangerous, so he didn't. He pushed it to be at most 120 volt. But if you have 120 volt and you need a lot of energy, that means you need to increase the current, right? So if you increase the current, that means you need more copper for the wires. So it's more expensive. So in Europe, they have decided to use 220 volt, okay, so more voltage, less current, so less wiring, so they save money. It's a good because there was a I don't know I think I will tell you about that, but there was a war. It was the current war between Tesla and Thomas Edison. Thomas Edison was not a very nice guy. He was a businessman, focused on money. Tesla was like his head in the cloud. Didn't care about money. He cared about science. So Tesla said the only way you can to transport electricity is to use AC, and he was right. That's what we are using now. Thomas Edison, he said, no, 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 no. I want to use DC. And to make his point, he will do horrible things like very famous video that you can still find on YouTube. Like take an elephant and electrocute the elephant in front of everyone on the TV. Right? So was not very nice. So why did I say that? Because in Europe it's 220 volt and here is 120 volt, right? You can look at that, the war between Tesla and Edison. Not very nice. So anyway, so we don't do that anymore because now we add another hose here that goes to the ground. So if there is a leakage somewhere, instead of going through you back to the base, it will go this way. So it's to protect us. Is that clear? So the hot wire is at 120 volt above the neutral wire or the return path. You see how it works? Now sometimes, so let me ask you something, sometimes you have 4 holes, right, in the outlet in the big machine. The washing machine, for example, you see how the outlet has four connectors? So what do you think the voltage is? You have 2 holes. So this one is 120, this one is 120. 240. So those big machines get 240 volt, okay, relative to the return path. And they also have a connection to the ground. Because those big machines, they have a motor inside. Each time you have a motor, that means it's consuming more energy. Is that clear? Okay. So let's try to do 3:30. We have to stop. Oh, by the way, you know all those problems, if you go in my Dropbox, there is one folder and I go over all of them. Okay, every single one. You have tutorials for them. So I'm not going to go all over them. Let's try to do one, for example. Number 1. So that will be the current, okay, available. That's your power supply. So what's the power rating of the motor? So power equals what times what? Exactly. Okay? So that's the voltage across the power supply. That's the current burped out by the power supply. So it's going to be 3 watts. Very good. So I look at my laptop. So I have a laptop. I bought it at Costco, by the way. They have very good deals sometimes. And my laptop, if you look underneath, it says 20 volt DC. So it means that the AC will turn into DC because a laptop does not like AC, it likes DC. And it says 3.25 amps. So when you buy like another charger, if you lose it, you want to make sure that you have the right wattage. So you want to make sure you know how to find the wattage of your laptop. How much is going to be the power on my laptop? Okay. It's going to be what? Very good. 65 watts, right? Who said that? What's your name? Steven. 65 watts. That means my laptop is consuming 65 joule per second. Is that clear? So if I plug my laptop all day long, okay, so one day, uh, one day is how many seconds? So it's 24 hours, and in 24 hours you have, in 1 hour you have 3600 seconds. Is that clear? 1 hour is 3600 seconds. One day is 24 hours. Okay, so the energy consumed by my laptop will be 65 times 24 times 3600 joules. Is that clear? So the unit is in joules. Now, usually if you want to have the unit in kilowatt hour, and we will review that next time, you need to find the power in kilowatt and the time in hours. If it's in joule, you just have the power in watt. So in joule, if it's in joule, the power is in watt and the time is in second. Okay, we talked about that last time. Is that clear? Okay.